Welcome back to the EasySpin Academy 2020. This is day 2 and it's the 4th session, which is session 10. In this session, we're going to briefly talk about RapidScan CW EPR. You might have heard about RapidScan EPR. It's a novel way of measuring EPR spectra with a lot increased sensitivity and of increased time resolution. And the commercial equipment is already available. In fact, yesterday, Bruker had a webinar explaining some of the advantages of RapidScan from the perspective of time resolution. You could head over to the Bruker webinar website and watch the recorded webinar if you want. So RapidScan uses field modulation, just like CW EPR, except with two crucial differences. First of all, the modulation amplitude is much larger. So whereas for CW EPR, you usually try to modulate with an amplitude that's smaller than your intrinsic line width, with RapidScan you modulate larger. And the second difference is that you're not just detecting the first harmonic, but you're just dumping and acquiring the entire time domain signal all the times. And this results in a higher time resolution and higher sensitivity. Now you get this time domain signal as a raw signal out of the spectrometer with RapidScan. That then needs to be converted to the actual EPR spectrum in a procedure that involves first some baseline correction and then a deconvolution step. And my understanding is that the software for these commercial instruments does that automatically for you. But then you will get an EPR spectrum that's exactly the same as the CW EPR spectrum, and with the usual caveats of don't saturate and so on. But the fact that you get that RapidScan EPR basically at the end gives you the same EPR spectrum you would get with standard CW EPR means that you can EasySpin just right out of the box for RapidScan EPRs as well. So if you have a solid state spectrum, use Pepper to simulate it. If you have a slow motion spectrum, use Chili. And if you have a kind of liquid limit spectrum, use Garlic for it. So basically, if you switch from standard CW EPR to RapidScan EPR, you have to buy some new equipment, but you can use your existing scripts and workflows with EasySpin. Okay, EasySpin therefore does not contain like a dedicated RapidScan simulation function. However, it has some lower level tools that help you explore and understand the raw signals that are acquired in RapidScan. And let's go look at those a little bit. So first of all, we're going to look at a function that's called block steady. And that is to simulate the RapidScan time domain signal that is actually acquired. If you modulate the field over a certain range that contains your spectrum, you're constantly exciting spins. And these excitations lead to a time domain signal that's periodic with your modulation frequency. And this is what block steady is simulating. Block steady is named this way because it just solves the Bloch equations, which are the fundamental classical equations that describe the dynamics of an electron spin, and provides the steady state solutions for those. So after turning on the field modulations, there's a few cycles of some initial transients, but after that, the response of the sample settles into some steady state response. And that's the one that's simulated by block steady. Okay. Block steady is not a clean simulation function. It's more of like a tool. So its interface is a little different, a little more rugged than for Pepper, Chili, and Garlic. It takes several input arguments, and it can only simulate a single spectral line for a spin 1/2. So let's take a g-value of 2. We also will need to know the longitudinal relaxation time. We can make this microseconds, 2 microseconds. So this is the longitudinal relaxation time. And then T2 is the transverse relaxation time. This is also in microseconds. This transverse. Okay, next we need an field offset, and when you sit at a specific field and you modulate left and right, you have to specify which field you're sitting at, how is that relative to where your resonance is. So now let's set the field to be perfectly on resonance with the absorption line of this single spin 1/2. So delta P0, which is the field offset, is set to 0. Then we need to specify the modulation amplitude. So how wide we're actually doing field modulation. And let's do 2 millitesla, which is about 20 Gauss. That is about as large as you can get with CW EPR if you have with the right resonator and modulation calls. But this is very typical, or even on the lower limit of what you can do with rapid scan. Rapid scan sweeps can go up to 100 Gauss. They just have much beefier modulation calls, of course. You can't do that with your normal tiny modulation calls that are built into our standard CW resonators. Okay, so this is the peak-to-peak modulation amplitude. And it's again in millitesla. Finally, we need the modulation frequency. And we can just use 100 kilohertz, which is a modulation frequency that's pretty standard for most samples in CW EPR, but can also work very often for rapid scan. And the last parameter we specify is the microwave field strength, so how much power we're actually putting on the sample. And let's start out with a very weak field, 0.01 millitesla, or which is 1/10 of a Gauss. Okay, let's simulate now using block steady. We're going to feed information about the spin system, so the G value, longitudinal relaxation time, transverse relaxation time, followed by the field offset, the microwave strength, the modulation amplitude, and the modulation frequency. So now you again just press Control Enter and then see what happens. Okay, we get a plot, which I should enlarge a little bit here to see what's going on. It plots one period of the modulation. So the horizontal axis is a time axis. Since we are at 100 kilohertz, the time axis goes from 0 to 10 microseconds, corresponding to one period. The bottom plot shows the modulation field. It's centered around 0, and it's starting out at +1 millitesla, so the modulation starts at the higher field than where we set the field, and then moves towards lower field until -1 millitesla, and then swings back up. And then this cycle keeps repeating and repeating and repeating. Since we're on resonant, we set up that the spin is on resonant, we will hit the resonance when the modulation field is 0. So that's represented by this horizontal line. And when that happens, at that point where the field hits the resonance line, that's indicated by the vertical line, there we actually get a response, right? And as you see, as we hit the spins, we get an absorption signal, but we don't sit on that resonance very long. The field moves towards lower fields, moves away from the resonance, and as a consequence, we get something that it's oscillating, and it's oscillating with increasing frequency as you move further away. This is very similar to an FID, except that the frequency is not constant. Now, when the modulation swings back up again, so comes from the low field side, goes through the resonance and towards the high field side, we see the same effect happening again. We hit the spins, it absorbs, and then the absorption kind of keeps wiggling around until it fades away, until we're far enough away, or it's decayed. So these are called the wiggles, and this is the raw signal. This can be transformed to an EPR spectrum of the underlying line. We'll see that in a bit. So maybe it's useful to change T2 and see what happens. Let's change T2 from 0.2 microseconds to 0.5. Run this. And now we see I've extended T2, and you see now that this decay, the wiggles here, extend much longer in time. And the time scale of these wiggles here, you can see it's on the order of, it's almost gone after 2 microseconds, but it's in the order of like half to 1 microseconds. That is directly dependent on T2. This is also, again, very similar to an FID, which we would measure in pulse EPR. Okay, now let's go back to 2.2 microseconds, recalculate the spectrum. Now let's shift where we sit with the field. Let's set it to, let's say, 0.8 millitesla. So basically we're setting the field 0.8 millitesla higher than the actual absorption. Yes, and if you run this, now let's look at the bottom. You can see the resonance line is now indicated at -0.8 millitesla, which meaning from our field, the resonance is actually downfield 0.8 millitesla. And if you do now modulation, the modulation will mostly be ineffective for the first part, but only when the modulation field goes negative will hit the spins, and it'll turns around and will hit the spins again. As you can see, on one wiggle has low frequency, another wiggle has a high frequency, and this is a result of the very slow rate change of the field for this one here. But as soon as we cross the second time, we change much more quickly. So that's why there is an increased frequency. So rapid scan is a very new technology for most of us. And this is just a function that helps you to learn more about it and try to understand the underlying physics, which is based on the steady state solutions of the Bloch equations. Okay, now there's a second EasySpin function that allows you to explore how rapid scan EPR works. And that is a function that converts the raw spectrum, or the raw time domain data, into the actual EPR spectrum. Basically performs the so-called deconvolution step. So I'm gonna again just copy and paste some code here. Let's see where we are, 9:30. Okay, copy paste some code. Let's walk through it, what I'm setting up. First, I'm specifying a G value of 2.023, so typical organic radical. The same T1 and T2 values we had before. I'm gonna go on resonant with my static field, modulate with 2 millitesla or 20 Gauss, peak to peak at 100 kilohertz, and use a B1 field of 0.01. And now, instead of just letting Bloch steady plot the results, I ask Bloch steady to return me the data. And T is the time axis, and then MX and Y are the absorption and dispersion signals, and MZ is the longitudinal magnetization. Now, in order to deconvolve this, we use a function called rapid scan to SPC, to spectrum. We need to feed it the combination of absorption and dispersion. As you might know, absorption is the response of the spin system that's out of phase with the excitation microwave, and the dispersion is the response of the spin from the spin that's in phase with the microwave excitation. So absorption really absorbs energy, and dispersion doesn't absorb it, just disperses it. That's why they're named this way. And you have to combine them into a complex number, like the overall signal. Let's call it MXY, which is MY plus 1I times MX. So this is when we're building a complex number here. 1I is MATLAB's form of representing the imaginary unit, equivalent to the square root of -1. So we need to combine the MY with 1I times the MX. And we're feeding this complex signal that combines absorption and dispersion into one array, into that rapid scan to EPR function. We also need to tell that function what modulation amplitude we used and what modulation frequency we used. And it also needs to know the G value. So again, this is not a fully fledged simulation function. It's just a basic tool to play around with rapid scan time domain signals and convert them to deconvolution. So it also only works for a single line. Okay, we can press Control Enter. And let's see what happens. We do get another plot. So on the top, it plots the input signals, which are the rapid scan time domain signals we've shown before. Before we only looked at the absorption signal in blue. That's still there, the absorption that comes followed by the wiggles both times. And the dispersion is now plotted in red. And you can see the dispersion is down for the first half, and it goes up for the second half. So it has a different symmetry. Now, if those two signals are then processed together with information about the modulation amplitude and modulation frequency, we get the spectrum shown on the bottom. And you can see that this method clearly extracts the absorption spectrum, a single line centered at 0, and the dispersion component of that, which kind of is derivative looking, but is not the derivative. So these are basically the two functions that allow us to do some basic rapid scan analysis. Now, maybe something that's useful in this context to mention, doesn't quite have to do with rapid scan anymore, is how you can actually apply field modulation. It's a given an absorption spectrum. Let's say you have an absorption spectrum and you want to simulate the effect of field modulation. How would this look like if you had done field modulation with it and you had looked at the first harmonic? There's a separate function for that, and that function is called field mod. And I'm going to briefly demonstrate how that works. Again, this is not directly related to rapid scan anymore. So we'll start again out with clearing things, clear CLC and CLF, where CLF stands for clear the figure. So we're going to plot. Now let's get some system parameters. And I've already predefined that, a system.g with an axial G tensor and just some convolutional broadening. We'll take some experiment parameters, expand absorption spectrum, so harmonic 0. And we're going to simulate the rigid limit spectrum and plot it with pepper. Well, if we do this, we get a standard axial absorption spectrum that does not look very remarkable. Now, how do we get the first harmonic spectrum for this? There's two approaches. Well, first, if your modulation amplitude for your standard CW EPR experiment was really small, then you literally just generate the first derivative. And you can also just calculate the derivative. And we're going to call this spec d for derivative. And there's an EasySpin function for that that's called deriv, where you feed the x-axis, which is b, and the spectral axis, and that should give you the derivative. Let's plot it and see how it looks. And there you go. That is the derivative, right? But sometimes you might be in a situation where you overmodulated, meaning your modulation amplitude was larger than the narrowest line in your spectrum. And as I mentioned yesterday, there might be good reasons to do that, especially if you're just fishing for a signal and you really don't have a lot of it in your sample. The risk, of course, is that you broaden features or details that you might be interested in. So there's a downside to it, of course, as well. So in order to simulate this overmodulation, we use this field mod function. And that field mod function, you need to provide some sort of modulation amplitude in millitesla. That's as usual peak to peak. Field mod, and you feed the x-axis and the y-axis of the absorption spectrum, the modulation amplitude, and you tell it which harmonic do you want. And we want the first harmonic, so 1. Okay, and now if we look at this, field mod has some built-in plotting capabilities. So again, it plots on the top the input original spectrum, and on the bottom the modulated spectrum harmonic 1, modulation amplitude 0.5 millitesla. So that's the base to peak modulation amplitude. No, this is the peak to peak modulation amplitude. Okay, it looks as expected. Now let's start over modulating. Say maybe 3 millitesla, 30 Gauss. And voila. As you can see, now this edge feature of the absorption spectrum, which is just give a single nice peak, is now broadened out substantially. And the high field region, what we call it the perpendicular region, is also very broad. But look at the scale here. We're at 15. If I reduce this back down to, let's say, 0.1 millitesla, the intensity is 2, right? So by modulating more, you get more intensity, but you distort your spectrum. That's just a brief note on field mod, how you can apply field modulation to generate an overmodulated spectrum to compare to your acquired overmodulated spectrum. So this is kind of all I wanted to demonstrate in this session. We talked about first the block steady function that is used to simulate a rapid scan signal. And then we talked about the rapid scan to SBC function that converts this signal to a spectrum. And then finally, we talked about how to use the field mod function to generate a so-called pseudo-modulated EPR spectrum starting from an absorption spectrum. Okay, we are now at 10:50. The next session will start in 20 minutes. And until then, just please feel free to explore the documentation or the script, or ask questions on Slido. I will be hanging out there and answer as much as I can. So see you back in 20 minutes for the next session on least squares fitting.